Hi everybody. For this YouTube, I'm going to talk about electromagnetic fields and waves, and the topic is going to be uniform plane waves, Series 1. Okay, just to be the introduction to uniform plane waves, and we will get into deeper of the reflected wave and incident wave and transmitted wave later on, right? Probably put in YouTube of uniform plane waves in series 2. So let's start with the basic idea of this one here. Well, when you're talking about electromagnetic field or electromagnetic waves, you know that is they have two components. One is the electric field, represented by E, and the other one is the magnetic field, represented by H. And refer to Maxwell equations that you know the relation between the electric fields and magnetic fields. That's related to each other when you have electric fields. Change with the time is going to induce the magnetic field, and also if you have the magnetic fields uh, vary with time, and then it's going to induce electric fields. And the Maxwell equation, you can find the relation between the electric fields and the magnetic fields by simple math. Curl E equal to negative mu partial derivative of the magnetic field with respect to time, where mu is the permeability, that's the represent the magnetic property of materials, and also curl H equal to J, which is the current density plus epsilon partial derivative of electric field with respect with time, and epsilon is the permittivity of materials. Tell you the property of electrical. And you can also represent J by sigma E, when sigma is the conductivity of material. Okay, so you have two equations, and I already talked about it before in electromagnetic. Now also you can write the wave equations in the term of only electric fields and only in the term of the magnetic field. And you have some factor here, J omega mu multiplied by sigma plus J omega epsilon. The same thing as the equation for the magnetic field. It's the same, right? J omega mu multiplied by sigma plus J omega epsilon. And these two terms come to play very important roles and can use a lot in electromagnetic fields and waves. If I represent this term by gamma, so gamma is going to have the real part, and imaginary part is the represented by alpha plus J beta, where gamma is the propagation constant. Is tell you how the waves, electromagnetic waves, propagate or moving. Okay, this one can be electric field, and this one can be the magnetic field, E and H. And also this one, the direction of the wave propagation represented by P, where P is the pointing vector. You can find from the cross product of E and H. And if you take a look at the unit of electric field, which is the volt per meter, and H is the ampere per meter, you end up with the unit watt per meter square. Is tell you they transfer the power per unit area, right? So that's define the Poynting vector. Now for the term alpha, we call it as the attenuation constant. Sorry, is in the unit of neighbor per meter. It tells you how fast the fields, both electric fields and magnetic fields, will be attenuated when it get deep into a material. Okay, that's why I have the Z here. It's just like for this one, it's just like the block of materials. You start with the electric field or E0. When it get in deep into material, is attenuated, or the magnitude is like decreasing, and that's represented by the term E0 multiplied by exponential negative alpha Z. Okay, if you have alpha to be large, this one is going to attenuate very quick. And for the imaginary part of your grammars, it's better tell you about the phase constant in the unit of radian per meter. Okay, and then I will show you example how to explain this one. And for material medias, we have a property of mu, epsilons, and sigma, where mu is tell you the magnetic property, where epsilon is tell you the electrical property, and sigma is conductivity of the materials. Okay, so this is parameters that will come to play around with the wave equations. And also, if you divide E by H, you know exactly that E has the unit of volt per meter and H has the unit of ampere per meter. When you divide, both, term together, it gives you the unit of ohms. They call intrinsic impedance, which is represented by square root of j omega mu over sigma plus j omega epsilon. Okay, so these properties, get into these equations. Okay, now let's take a look at the simple system. When you have the lossless meter, that means your sigma equal to 0. You have no loss in the material at all. So from your propagation constant gamma equal to square root of j omega mu multiplied by sigma plus j omega epsilon, when your sigma equal to 0, you have your gamma become j omega square root mu epsilon. Okay, so your alpha, the real part, is become 0, and this become the imaginary part is give you a beta. Okay, so your beta equal to omega square root mu epsilon. When your alpha equal to 0, it means your fields is not attenuated. When you have your E0 to be the magnitude of your fields, it still become constant all along inside the material. And for beta, it gives you what? Your beta simply become 2 pi over lambda. From this equation, you can find the velocity of the waves into any kind of materials. When you have a beta equal to 2 pi over lambda, you multiply numerator and denominator by frequency. The denominator, you're going to have 2 pi f equal to omega, and denominator lambda f simply become v, so you can find the relation omega over v is equal beta. When you know beta, you can find the velocity of the waves in that materials or in that media. And in this case, since you're talking about the lossless meter, sigma equal to 0, So you have beta equal to omega square root mu epsilon. And if you find the ratio between omega and beta, it gives you 1 over square root mu epsilon. In case of the free space, you know that mu equal to mu 0, epsilon equal to epsilon 0. So you just plug in the number here, become 1 over square root mu 0 multiplied by epsilon 0, where mu 0 is equal to 4 pi 10 to negative 7 Henry per meter, and then epsilon 0 is equal to 8.85 10 to negative 12 farad per meter. It's going to give you the number is about 3.0 10 to the 8 meter per second, and that's the velocity of the light. Okay, so that's give you c. This is how you find the velocity of the wave in the media. Now take a look at the intrinsic impedance. When your sigma equal to 0, you end up with eta equal to square root mu over epsilon, and equal to mu 0 divided by epsilon 0. You do the same thing, plug in the number mu 0 and plug in the number epsilon 0. You end up with 120 pi ohms, or it's about 377 ohms. So this one gives you it's about 377 ohms or 125 ohms. That's what we call our eta 0, or intrinsic impedance of the free space. Now take a look at example here. You have electric field is 10 volt per meter. From this relation here, you can also find the magnitude of the magnetic field. Simply divide electric field by 120 pi ohms, and it's give you I don't have the calculator, so I just leave, just like this one here. Now for uniform plane wave for frequency equal to 1 gigahertz, epsilon r equal to 2.1, or relative permittivity, and relative permeability equal to 1, and your conductivity is about 0. Find velocity of the wave in that media. Find intrinsic impedance, beta, the phase constant, sorry, and the wavelength. Okay, let's start with the velocity. You know that velocity equal to omega over beta, and your beta is equal to omega square root mu epsilon. So your omega cancel out, and you have omega equal to omega r, omega 0, epsilon equal to epsilon r, epsilon 0, and I can split this term, and 1 over square root mu 0 epsilon 0 simply become c, or it's about 310 to the 8 meter per second. Or this one sometime you can write is in the term, I do have here, v equal to c over square root mu r epsilon r, or relative permeability and relative permittivity. So you can see that since mu r and epsilon r is never be greater than, never be less than 1, so your v is always less than or equal to the speed of light, c. Now for lambda, you can calculate from v equal to f lambda, give you 20.7 centimeter, or you can calculate directly from beta equal to 2 pi over lambda. So your lambda equal to 2 pi over beta, and your beta is equal to omega square root mu epsilon. So your 2 pi cancel out. You also have your lambda equal to c over f, and if you calculate this one c over f, you can even write in the term of lambda 0. Okay, and you divide by square root mu r epsilon r. So your lambda is equal to 20.7 centimeter. The same thing. Okay, so now your beta is equal to omega square root mu epsilon. You just plug in the number. You get a 30.4 radian per meter. You want to change this one into term of degree. So you multiply 30.4 by 360 over 2 pi. Okay. You end up with 1740 degrees per meter. And what does beta mean? It means like if you have the wave coming into media, when you get deep into the media here, in the distance 1 meter, your phase gonna change 1740 degrees or 30.4 radian per meter. You get deeper into the media, your phase gonna be much different. Okay, you can calculate from that, because the unit of beta is the radian per meter. Or you can calculate directly from beta equal to omega square root mu r epsilon r multiplied by square root mu 0 epsilon 0. And if I pick up this term here in the red line, put this is the beta 0. So it just multiplied by the factor of square root mu r epsilon r. Now for the intrinsic impedance, since your sigma equal to 0, you end up with square root mu over epsilon, and you split this term, you get this term become eta 0 or 120 pi, or intrinsic impedance in free space, and you will multiply by the factor square root mu r over epsilon r. You have your eta become 260 ohms. And keep in mind that your impedance is allow you to find your relation between E and H. Okay, when you know E, you can find H. Simply multiply by eta. Now, when I talk about the wave equation with the parameters gamma or the propagation constant and your eta, which is the intrinsic impedance. Earlier I'm talking about lossless media, sigma not equal to 0, sigma equal to 0. Now you take a look at the case of lossy media when sigma not equal to 0. What gonna happen? You're going to end up with your gamma is going to end up with both the real part and imaginary part. So you have both alpha term and beta term. Same thing as the intrinsic impedance. You're going to end up with the real part and imaginary part. Okay. Now take a look at the example. For the copper block, you have the frequency 1 megahertz and sigma equal to this is the conductivity of the copper is equal to 5.8 10 to the 7. Epsilon r is about 1, mu r is about 1. So you can calculate your gamma here. Just plug in number. Okay. Follow the equation here. You end up with your gamma equal to 2.14 10 to the 4th, and the phase angle is 45 degree, or your real part is become when you have the phase angle to be 45 degree, you know exactly that the real part has to be equal to the imaginary part, which is equal to 1.513 10 to the 4th. And you can calculate your V directly from omega over beta. You know the frequency is 10 to the 6 hertz or 1 megahertz. You divide by beta that you already have here, and you end up with your velocity to be 415.3 meter per second. You notice this number is very low compared to the speed of light, because when the wave get into a conductor, because copper is very good conductors, and it seems the speed of the wave is slow down a lot. And now you take a look at the intrinsic impedance. Just plug in the number, follow the equation eta equal to square root j omega mu over sigma plus j omega epsilon. You end up the same thing, eta equal to 3.689 10 to the negative fourth, and the phase angle to be 45 degree. Okay. I just want to point out, what we get here. Since you have the relation, the magnitude of electric field over the magnitude of the magnetic field equal to intrinsic impedance. But in this case, when your sigma is not equal to 0, you end up with the intrinsic impedance become a complex number with the phase angle to be 45 degree. And this tell you that the electric fields of the forward propagating wave will have the phase 45 degree leading the magnetic field phase, right? So this is, you have the 45 degree in here, so that means your phase will lead the phase of the magnetic field by 45 degree. Okay, and we will see more example related to the phase different here. Okay, now for the attenuation constant. You have alpha right here. Just want to point out, why it's so important. Okay, take a look at the relation between electric field and Z deep inside material. Okay, you have the plot between the magnitude of electric field, and it starts with the E0. When it gets deep into materials or media, it's going to be attenuated, by the factor exponential negative alpha Z. And if I want to write the magnitude of electric field in any location in the media, I have this one here, Ez equal to E0 exponential negative alpha Z. For example, if I want the magnitude reduces by the factor of 100, I can find the distance from the surface of the meteor that's going to give you reduce the magnitude of electric field by the factor 100. So I simply divide E of Z by E0 and make it equal to 1 over 100, and that's equal to exponential negative alpha Z. And what I did is just like I move exponential on the right to the left, so this become the sign to be positive, right? And I move 100 up here, just to make you easy to understand. And I apply ln both sides of equation, so I have Z alpha, correct, equal to ln 100. So I simply find Z by divide ln 100 by alpha, so I get the D equal to 3.04 10 to negative 4 meter. And keep in mind that this is also the frequency dependent, because you have the alpha here is also depend on what frequency, right? Because you get your alpha term from what? From this equation here. You take the real part, it's going to give you alpha. So you have frequency here, okay? Okay, now take a look at the power flow. Since you already know that the electromagnetic wave is going to propagate in the direction of E cross H, and that gives you the direction of the power flow. So the power flow is depend on the magnitude of electric field and the magnetic field. Have this term. Okay, I'm not gonna explain this one a lot, just bring this up to you. So it's also the time average power density is also a vector, simply equal to 1 over 2, pick up the real part of E cross H conjugate. For this example, just to make it simpler, if I have the electric field, have the component in the x direction only, and magnetic field, I have the component in y only, and you have the relation between E and H equal to eta, and the time average density in the forward traveling wave, I put is average, put the positive sign, is mean move in represent forward traveling. It's equal to 1 over 2 EM positive, or the amplitude of the electromagnetic wave square, divided by eta, intrinsic impedance of the meteor, and also multiplied by exponential negative 2 alpha z. The attenuation constant also come to play, roles in the equation, or time average power density. And you also need to multiply by cosine theta, the phase angle of the intrinsic impedance. And for reflected wave, okay, I put this negative sign here. It's equal to or negative 1 over 2, because it's moved back to the opposite direction of the forward traveling wave. Okay, this one move to the positive z direction, and this one have to move in the negative z direction. And you put there E, the magnitude of the what you call reflected back wave, is become EM negative square divided by intrinsic impedance, same. And this one is look exactly the same thing. You just change the amplitude here to give you is average. Actually, this one's vector. Okay. And if you notice, when E has the component of in X and H has a component in Y, and the Poynting vector is simply equal to E cross H. Okay. So it's become E has component AX. So you have AX cross H in the direction of Y, right? So become AX cross AY. That's why you end up with AZ. It's tell you the direction of the wave, moving, and it's become AC. Now for the lossless meteor is means sigma equal to 0, and your alpha, I talked about it before, alpha becomes 0, and your eta, it just become real part only, have no imaginary part. So your theta, eta is simply 0, and this one also 0. It gives you 1, right? And you don't have this alpha becomes 0, so you don't have this term. So it's end up with the, for lossless media, you have its average become only 1 over 2 EM square over eta. Okay. Now, sorry, for the case you have the electric field to be 100 volt per meter, frequency 300 megahertz, is lossless meteor. Okay, lossless meteor implies that your sigma equal to 0, and epsilon r mu r is given. This one is sigma equal to 0. Okay, so you find your eta simply equal to square root mu r over epsilon r multiplied by intrinsic impedance of the free space, which is equal to 120 pi. you end up with 40 pi, or it's about 126 ohms. And then this is when or you can put this is the phase anchor to be 0, as I mentioned before, when you want to calculate the S average. And also beta equal to omega square root mu r epsilon r over c. You plug in number, you get beta equal to 6 pi radian per meter. Now you want to write the electric field equation and the magnetic field equations. You can do that by pick up the equation E equal to E0 cosine omega t minus beta z. And as I mentioned earlier, that electric field has the component only in the x direction. Now you are plugging E0 is the 104 per meter. Omega, you know, that's equal to 2 pi f. This is the frequency, 300 megahertz. And your beta, you already have it here, so it's become 6 pi. And with the direction in the x direction, become 4 per meter. This is your E. Same as H. H, you bring up the relation, the ratio of electric field and magnetic field is give you eta, intrinsic impedance, right? So that's why I have H equal to E over eta. So it come 100 divided by eta. What is your eta? You already calculate, you know, from here. So you plug in eta equal to 126 ohms. And cosine omega t minus beta z, you have no phase difference between E and H because your phase anchor is 0 from your intrinsic impedance, because it has already the real part. Then H equal to 0.8 cosine 600 pi 10 to the 6 t minus 6 pi z ay. And you can find from that, you can find the S average to be 102 em star square over eta az. So your m is 100 and eta is 126. You end up the S average to be 39.79 az, watt per meter square. Now what happens if your sigma is not equal to 0 but equal to 10 Siemens per meter? Use the same condition as the previous example. Well, you start by calculating, you know, eta, plug in our number, because your sigma is not equal to 0 but equal to 10 Siemens per meter. You have to calculate all of this. So you end up eta become 15.4 with the phase anchor to be 44.57 degree ohms. And now you're gonna have the phase lag or the phase difference between electric field and the magnetic field. And also you calculate for propagation constant gamma. This give you 153.91 with the phase anchor 45.43. And if you expand this term, this give you the real part and the imaginary part. The real part give you alpha or attenuation constant, and the imaginary part give you beta or the phase constant. Okay, you have no problem to find eta, you have no problem to find gamma. Okay, just use your calculator. The difficult task is that you have to do the square root of the complex number here. Now you want to write the equation for electric field and the magnetic field. What you can do is going to be your extra term here, exponential of negative alpha z for electric field. But you have no problem because your alpha you already calculated, you know, become 108.01. So you just plug in the number right here, and you still have AX because the electric field has the component in the X direction, 4 per meter. Now for H, it look like you have this term same thing, but you also have the phase different, and you pick up the phase different here from your eta that you calculate earlier here, 44.57. So you have 44.57 degree right here, and in the component of y direction. Okay. Now for the S average, you have this term also show up when your theta n is 44.57 degree. So you just add this term up, and you get your S average to be different than the previous one when you have sigma equal to 0. Okay, so this is gives you the idea, how to calculate the S average. Now when we talk about your gamma and your eta, in that case we are talking about sigma equal to 0. It seems to be for the lossless material. But if you take a look at the condition in general, when you're talking about a good dielectric, we also have to consider the ratio of the sigma, or the conductivity, divided by omega epsilon. If it's become much less than 1, we consider that media is the good dielectric. But if the ratio of sigma over omega epsilon much greater than 1, we consider that media is the good conductor. Okay. Now in math, because we have to go through the calculation of gamma and eta, because it's associated with the complex number, square root of the complex number. But I just bring this up. For good dielectric, the ratio of sigma over omega epsilon much less than 1. Using math, your alpha become sigma over 2 square root mu over epsilon with the condition here. Okay, you can play around with the square root here. And actually is something look like 1 plus x to the power of n, and if x is much less than 1, you can expand this one to be 1 plus n divided by x plus n over multiplied by n plus 1 x squared over 2. But since the x on this one is much less than 1, you can ignore this term. Okay, so you can have the real part and imaginary part. So your alpha end up to be sigma over 2 square root mu epsilon, and beta simply you can approximate to be omega square root mu epsilon. What about eta? It's become the ratio of j omega mu over sigma, and sigma plus j omega epsilon, or you can put this one as the square root mu over epsilon. And for good conductors, when the ratio of sigma over omega epsilon much greater than 1, you consider this one, you consider this meter to be your good conductor, and you end up with gamma equal to square root mu omega sigma, and the phase angle 45 degree. When you have the phase angle to be 45 degree, that means you have the real part equal to the imaginary part. So that's why you have alpha equal to beta. So it's approximately about square root omega mu sigma over 2. Same thing as eta. It gives you a square root omega mu over sigma, and the phase angle to be 45 degree. Well, if you take a look at the ratio of sigma over epsilon, since omega is 2 pi f, it's become the frequency dependent. For this case, it doesn't matter what your sigma is, it doesn't matter what your epsilon is. You can change your media to be good dielectric or good conductor, depending on the frequency. Okay, for the case, if you have the frequency is very large, this term is getting smaller, right? So it's become this case. But when your frequency is smaller, this term become large, and this can turn out from the good dielectric to be a good conductor. Okay, so please keep that in mind. Now go take a look at example. For a copper conductor, you have sigma equal to 5.8 10 to the 7 Siemens per meter. Epsilon r is about 1, and mu r is about 1, and the frequency is 60 Hertz. You can check the ratio of sigma over omega epsilon. Just plug in all the number given. So I have this one to be 1.74 10 to the 16. That means it far, r is larger than 1. So it's become good conductor. You can pick up your alpha and beta, and your eta you can pick up from this here. So you calculate alpha equal to beta, you send up to be 117.21 per meter, and your eta is there equal to 2.86 10 to the negative 6, with the phase angle is 45 degree. And now from beta here, you can find your lambda by the relation lambda equal to 2 pi over beta, right? You already know this one here. And you plug in beta, 117.21. This gives you lambda to be your 5.36 10 to the negative 2 meter. When you know lambda, you can find velocity of the wave in that media. Simply multiply lambda by frequency, and you know frequency already is 60 Hertz. This gives you a v equal to 3.216 meter per second. It's very low, it's very small number compared to the speed of light. So because this is in conductor, and copper is a very good conductor. Okay, now let's take a look at the frequency as 10 gigahertz. You plug in the number, you have omega, you have the 10 gigahertz here. The ratio of sigma over omega epsilon is still far beyond 1, or much greater than 1 is still become a good conductor. So you would repeat calculation just like the previous example. Okay. But if I change this one to be a very small frequency, it might turn this media, instead of good conductor, it might be a good dielectric. Okay, keep that in mind. Okay, the last one I'm going to finish up with the skin depth. What does it mean, skin depth? Skin depth means when you have the wave, electromagnetic wave, get into a media or some kind of material with sigma is not equal to 0, it's going to attenuate when get deep into the material with the relation the magnitude of your fields equal to E0 multiplied by exponential negative alpha z. And if the ratio drop to be by factor E, you can calculate z, or the location or the depth into the material. That's give you the ratio of the electric field, or reduces by the factor 1 over E, and that's what we call the depth of penetration, or skin depth, which is simply become 1 over alpha. For good conductor, you know that alpha equal to square root omega mu sigma over 2. So your skin depth delta equal to square root 2 over omega mu sigma. So what is so important about the skin depth? Well, you take a look at a conductor. When you have the interference signal or noise, whatever is coming in, you don't want to have electromagnetic interference. You can insulate some kind of material, by a good conductor, because it will get rid of your electromagnetic wave. It's just like the electromagnetic wave shield. So help shielding. That means your electromagnetic fields is going to be reduces very quick. Okay, so that's one of application. That's why the skin depth is very important. Well, for the next YouTube, I'll probably be talking about incident wave. When you have two media, 1 and 2, with the different media property, that's mean in the term of mu and epsilon and sigma. I will explain when you have the incident electromagnetic wave, okay, which have the electric field and the magnetic field component. It's going to reflect back. So I have the electromagnetic field reflect, represented by R, and also you're going to have the electromagnetic field transmit into the second media. So I put this one as EMT. Okay, we will talk about in the next YouTube.